Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, for those of you that were here last year for Jeff's initial talk, this is some follow work from Jeff Dozier from UCSB, who had done some work on the Snowpack, but wanted to kind of update us on the latest activities from his visiting portion this year. So, thanks, Jeff.
Okay. Yeah. I've decided I like this title of being an intern. This is sort of good. So. All right, so what we're looking at is the idea of trying to really do snow hydrology in areas where it's the runoff from snow is really important, and yet there's not much of a surface infrastructure to really make any sort of measurements. So this is the Hindu Kush range of Afghanistan. We're looking at an area that's 8 times the size of the state of Washington. So it's, we're trying to run these models over pretty large areas. Okay, and the problem that we face, or that the people there face, is illustrated by this this advisory that came out from the UN's information on our Institute for Regional Information Networks that sort of monitors conditions all over the world and tries to sort of alert the international community that if something is troubling. And you can see this is a fairly sort of desperate warning. And the problem is, if you look at the date on it, it came in September after the harvest had failed. And so the question is, could you have done a better job? And even looking at passive microwave data, we see that this year in this basin, in terms of just the total amount of snow, it was a pretty low number. And so the idea is that we could have given that warning in April rather than in September, and therefore could have better organized a response to it. And in fact, it was ironic that the following winter, in 2012, was a fairly big snow year, and this caused the problem of not being able to get food supplies into places where people were starving. So 1 year of not enough snow, and then the next year of too much snow, and the combination of those led to a lot of starvation. Okay, so the problem with this, though, is one of the questions is do passive microwaves, in fact, give you a reasonable signal of the snowpack in the mountain environment? And so we've done some of this work in the Sierra, where we've got measurements at the surface to compare with.
Jeff, back up. So how do you do these passive microwave measurements?
Oh, so what a passive microwave signal does is
Like planes flying over?
no, it's satellite.
Satellite?
Yeah, and it's 25 kilometer pixels or so. The reason is that the emission from Earth's surface at those long wavelengths is very small, so you're not getting many photons to count. So the only way to do it is you got to open up the. You can't get a very good resolution. The principle on which it operates is in the microwave part of the spectrum. Snow is not very, ice is not very absorptive, and so what happens is, but it does scatter the radiation. So you get radiation that's being emitted from the soil, and then it's being scattered by the snowpack above it, and scattering, of course, causes extinction, and that's why, a cloudy day, there's less sunlight under the clouds. And so what happens is that by looking at the emission from the longer wavelengths where you're seeing through the snowpack and then looking at the shorter wavelengths, you're actually trying to estimate how much attenuation is coming from the snowpack and therefore the snow water equivalent. Now the problem is if you compare this with a method called reconstruction that we've worked a lot on, you can see that it's an order of magnitude less if you look at the numbers on the y-axis. So in the mountains at least, the passive microwave estimates are only seeing about 10% of the total volume. And there's some physical reasons for why this. And so therefore we've tended to focus on this idea of reconstruction. But you can see this problem. This is a time series map of the passive microwaves. Let's see, I'd like to just make it go a little faster, but okay, this is a daily map. And we know snow doesn't really behave this way, right? It's, flickering on and off. And so one of the questions is, well, are there ways that we can still use it? And in order to figure out that, we have to have ways of estimating the spatial distribution of snow. So the way I do this is I've got the passive microwave data over here. The nice thing about them is they're timely. You get the estimate of the snowpack right away, but a lot of uncertainty and very coarse resolution. From MODIS, or from other satellites, but from MODIS, I can get estimates, daily estimates of snow cover and the reflectivity of that snow. And then from the global land data assimilation system, we can estimate solar radiation and long wave radiation and so forth. And therefore, we can put that all together and we can model the snow melt day by day. Now we can't tell with this how much snow there is because in this part of the spectrum we don't see through the snowpack, we just see the surface. But on the other hand, if you can model the melt and if you can tell when it disappears, then you can back up that calculation and figure out how much there was on a previous day. And so the idea is to do that, we want to get then an estimate of the snow water equivalent, trying to figure out if we can correct for the passive microwave data. And then the way that this is will be used in an operational sense is we can put that year into the historical context. Automatically we can sort of say, well, is there reason for concern or not? And if the answer is yes, then the Army takes that information and looks at what happened in previous years and then issues warnings. So now what I worked on for this summer is a computationally intensive part of the problem, figuring out how to try to use cloud computing to help with this. And the issue is I actually need to have a daily value of the snow-covered area, and along with that I get an estimate of the grain size and the albedo. So how do we do this? Well, we start with we kind of try to go to basic physics. So this is a graph of the optical properties of ice and water, and this is the index of refraction, the kind of thing you learned about in high school about how light bends when it goes through a substance. This is the absorption coefficient. And I've actually got a slide that kind of explains what these are. This is what the refractive index, the definition of the refractive index, how the light bends as it goes through a material. This is the definition of the absorption coefficient. That is, you get a decay as you're passing the light through a pure substance, and you normalize it by the wavelength so that the absorption coefficient can be dimensionless. And then if you solve that differential equation, you get
I found you.
hello, Tony. So we were just defining the absorption coefficient.
Oh, very good.
So we get an exponential decay. Now, in order to kind of explain what a number of an absorption coefficient might mean, I simply can take this exponent and solve for the distance at which this number is going to be -1. And so we can call that an E-folding distance for light as it's passing through snow, or excuse me, through pure ice. So, oops, let me back up and do that. And so what we see is if we look at the E-folding distance for ice, that it varies by, 7 orders of magnitude over the distance of the solar spectrum. So in the visible part of the spectrum, that number is, tens of meters. So, when you go diving in Hawaii and you're under the water, you can see a long way. And similarly, if you were frozen in bubble-free ice, you'd also be able to see a long way. Whereas when you get out to the longer wavelengths, that number, gets down to less than a millimeter, right? And the consequence of that is we can then, put those kinds of numbers into a calculation of the scattering properties of an individual snow grain. This used to be a really interesting and difficult computational problem. That is, Gustav Mie published his equations in 1908. The first really fast and useful solution to those equations by computer was published in 1980, 70 years after the equations themselves had appeared. But I don't have to worry about that. That's been done now and been done really well. But what you can do then is take those properties for scattering from a single grain, and you can do a multiple scattering solution for what's going on in the snowpack. And what you end up with is something that is intuitively pretty obvious. And so what this graph shows is the reflectivity of snow, of deep snow, for the wavelengths of the solar spectrum, for a variety of grain sizes, going from very fine grains to coarse grains.
And 0.05 deep powder.
Pardon?
0.05 best for
0.05 is pretty small. Yeah, that's about as small. Maybe 0.03 is about as small as snow gets. And then on the right-hand y-axis, I've got that absorption coefficient plotted. And what you see is where the absorption is low, the reflectivity of snow is really high, and it's not very sensitive to the grain size, right? Okay, and snow is, across the visible spectrum, snow is white, right? And it's white. But if you look at an individual snow grain, it's not white, right? It's transparent, right? And so, but the multiple scattering makes the reflection white. So, if a child asks you, where does the white go when the snow melts? Well, you've got a way to answer it, right?
It turns black in my driveway, actually. I have an actual question. Is there an intuitive reason why certain wavelengths have, at the high end of wavelength, have those weird spikes? What is that?
Oh, those are rotational and vibrational moments in the quantum mechanics of the absorption of ice.
So rotational states of the water molecule, is that that?
Well, or of the ice molecule. But these are pretty. Ice and water are only shifted a little bit in this part of the spectrum. Whereas out in the microwave, ice and water are really different, right? But what you see here is a couple of things. One is, as you get out to the region where the absorption is moderate, then the grain size makes a difference. So what happens as a result of that is, as the snow ages and the grains grow, it becomes less reflective. Because remember that about half of the sun's energy is out beyond the wavelengths of the visible. And then out here, snow is pretty dark. And that helps us distinguish snow from clouds. Because clouds have little particles. That's why they're still up in the sky. I mean, that's really the difference between an ice cloud and a snowpack. A snowpack is a cloud that got big enough, where the particles got big enough that they fell out of the sky and landed on the ground, right? Okay, so what this means is that if you compare snow to the other things that occur on Earth's surface, here's vegetation, here's different kinds of soil. First of all, there's a lot of variability in snow. If you go out beyond the visible, snow is one of the most colorful substances in nature, right? But you also see that if you compare it to the wavelength bands of MODIS that are here, that it really is distinctive. It allows us to distinguish snow from the other elements. And out here, we can distinguish it from clouds. In other words, snow is about the only thing that is really bright in the visible part of the spectrum and really dark in what we would call the shortwave infrared, and sensitive to grain size in the middle between those. So what that allows us to do then is, if we have satellites that have this sort of spectral information, we can distinguish snow from other substances. And this is with Landsat, and this is very nice. This is at 30-meter resolution, but it's got a 16-day repeat pass because the swath is only 185 kilometers, and so therefore you miss opportunities. So a lot can happen in 16 days, and if that day happens to be cloud covered, and now you're 32 days between acquisitions. So we'd like to do something a little better, but this use of the shortwave infrared part of the spectrum allows us to distinguish clouds. So here's the visible bands, and you can see the clouds and the snow are a little hard to tell apart. But there's if you use the bands out in the further into the spectrum, you can see that the clouds are pretty distinctive.
The clouds of the blue?
No. The clouds
Never seen blue snow.
Well,
Is that Eastern Sierras?
That's Mono Lake.
Mono Lake.
That's
Ah, so, okay.
All right. So now what MODIS has is it's got very similar bands to what's on Landsat, but it's got a swath of 2,300 kilometers. And so this is a MODIS tile that is 1,200 by 1,200 kilometers. So that's 1.44 million square kilometers. State of Washington is 180,000 square kilometers. So this is 8 times the size of the state of Washington. So, and this one we get daily coverage, all right? But the spatial resolution is 500 meters. And so what we're able to do is, with this spectrum, we can get around this, or we can at least compensate for this coarser spatial resolution by estimating a fractional cover of snow within each pixel. So what this does is we can calculate what are called end members. In this case, this is the green is the concentration of the vegetation, the red is the concentration of soil, and the blue is the concentration of snow. And so we can solve for each. That's also a pretty computationally intensive problem, but it can be done as a parameter sweep. Because each pixel's computation is separate from the neighbors. So it's a nice application for trying to put onto a cloud, right? And it works pretty well. This is comparing what we get at 500 meters with what we get from 30 meters, and this is the scatter diagram. All right. So there's some things I want to do with this part of the process, but that's not really what I focused on this summer. The problem is I do want to get a measurement every day. And sometimes what you see is you get clouds. And so what I'm thinking here of, this is now a data cube. So this is the plane is the spatial dimension. And it's in a projection, so these are kilometers north and south on the left and east and west, and then date on that axis. And the red color, it shows the absence of data. So I picked it. I'm not sure it was a great choice, but on the other hand, there's holes in my data, so it's bleeding, right? And so we can look through the year, or in this case, just a 32-day period, and then so my first step is in trying to get to the daily data is to use a three-dimensional Laplacian to try to fill in those holes, right? But I don't change any of the observations themselves, okay? And you can see that, we get something where the holes are all filled in, but where it still looks pretty messy, all right? So we need to have, and this is the thing that makes it kind of a tough, a harder computational problem, is that these really are three-dimensional data where there's lots of neighborhood effects, because sometimes we want to slice the data this way, sometimes we want to drill down through the column. And so in trying to sort of fix this, to make it smoother, we want to be able to use some knowledge about what we have. So there's a couple of different kinds of glitches in the data. This is a pretty clear day. So what we end up with, though, is we have both low frequency dropouts caused by the clouds, but we also have high frequency because one of the MODIS bands is starting to go bad a little bit. It's got some periodic noise in it, indicated by these little red dots. And if we look at it if we zoom in on some of these areas, we can see, again, both this low frequency noise that we can identify, but also some high frequency noise. So, and not only that, we see this this break in this image right in the middle of, and what the reason for that is in this case, this image was stitched together from two different orbits. So part of the cause of this variability is the fact that we're getting this wide swath, of more than 2,000 kilometers from only a 700 kilometer orbit. And so that means you got to be looking at things at a pretty high viewing angle, right? So this is a map of that images, and it's what we would call the sensor viewing angle. So that's the angle up to the satellite if you were standing on the surface. All right? So it's if it were a plane parallel system, that would be the same as the nadir angle from the sensor, but because the Earth is curved, those two numbers are different. Now the problem is what happens as so where it's blue, it means that that place was right underneath us at this time of the orbit. Where it's red, we're up to 60 degrees or so off the zenith when we're looking at it. And this thing in the middle is where the two orbits were stitched together. So what that means is that at the edge of the swath, so the pixel right underneath the satellite is half a kilometer square. The pixel at the edge of the swath is about 5 times 1 kilometer. So it's 10 times as the area at the edge of the swath. So that's part of the problem that is introducing some of this noise into the image, is that on different days you're actually looking at a different piece of real estate on the ground and you want to try to put together how do you put a picture together? So I think what this is, it's a class of smoothing problems that where I have more confidence in some of the data than I do in other measurements. And so I want to adapt a smoothing method that in fact takes advantage of the fact that I have a physical reason for having more confidence in some points than others. And so what I do is I actually use a smoothing spline, but I weight the smoothing spline inversely to that viewing angle. Were you raising your?
Yeah, you have to deal with the deeper air column and then more moisture. Is that?
Oh, that we actually start with an atmospherically corrected value. Yeah. But so I guess the point is that if I have a bunch of clear days, then the off-nadir shots don't contribute very much to the signal. They pretty much get ignored in the smoothing algorithm. But on the other hand, if that's the only view I have in a 2-week period, then I'll use it, right? Okay, so this next. So that's what results. Okay, so.
This is after smoothing?
This is each. So that's the first time I've seen it. So. Okay. So what it is it's that same cube that we looked before,
Sure.
And it's showing every day from over a 32-day period.
As a result of the smoothing that you...
As a result of the smoothing. But I think it's pretty good.
Yeah. Yeah, it actually looks much better than the other cube.
Yeah. That's the idea, yeah. So it,
Yeah, definitely. You can see there's, where before they would just flicker on and off.
yeah, no, okay, so it works really well. I'm really pleased to have done this. The only problem is this is just 800 pixels by 800, and it's only a 32-day slice. So this is a 1/9 of a MODIS image and a 1/12 of a year, and this took about 2 hours.
Computationally, or
Yeah.
so in clock time, wall time, the Azure process takes 2 hours.
Well, actually, I ran this just on one node, but I know now how to break this up, and Wen Ming's here, and we're going to do that. I've got another week. In other words, what I'm going to do is use. So I do the Laplacian smoothing over the full tile, 2400 by 2400, and then what I'm going to do is divide that into 9 parts, and then take the whole year column and do the smoothing on the whole year, and that's a way of getting by the of actually taking advantage of multiple things. Okay, and then the way that the reconstruction works is once I have that, then I can run a snowmelt model, and the way I do that is this is illustrated with measurements from a snow pillow, that if you don't have a snow pillow, but if you know what day the snow goes away, and you can calculate the rate of melt, then you can back up and figure out how much there would have been. And so this gives us a couple of things. It gives us a spatially distributed estimate of how much snow there was back to about the peak of the snow cover, right? And so that allows us then to compare with passive microwave data. It also allows us to compare with models, because one of the problems especially in precipitation models is you've got a grid, you're modeling at some spacing on the grid of 10 kilometers or 150 kilometers or something like that. And how do you compare that to a measurement? What is it you compare to? Well, now we've got something that we can use to compare. So the way this works, we've compared this in the Sierra, where we've got surface measurements, with measurements at snow courses, which are the ones done monthly by people skiing through the mountains and poking a tube in the snow and weighing it, and then also with snow pillows, which are an automatic measurement. And the good thing is, obviously there's some error in that, but the error is centered around 0, so there doesn't appear to be a bias, right? And part of the error is that the snow pillow is only representing a point within a half a kilometer pixel. So the snow pillow is not a perfect measurement either, right? And then if we compare to the inputs from, we estimate the incoming solar radiation pretty well. Air temperature, we do pretty well. A little bit of a bias in the incoming long-wave radiation. That could also be a measurement problem. That's a difficult thing to measure at the surface. And in the Sierra Nevada, there are really only 3 long-term stations that do it. Well, the reason it's difficult is that you're measuring the same thing. Your instrument is emitting the same thing you're trying to measure. And so the temperature compensation has proved to be hard with those. Okay, and so is this reconstruction giving us a good answer? Because we have other methods, at least in well-instrumented places of getting alternatives. One is if we have a lot of surface measurements, we can just do a spatial interpolation. Or if we have a lot of surface measurements, we can do a data assimilation model. And the reconstruction is, in fact, showing greater amounts of snow than any of those. So are we right, or are they right, right? And here's our estimate that shows that the reconstruction is right. So what we've done is to use the stream flow in these basins, do a calculation of evapotranspiration, and then how much change in storage it is. In other words, taking the hydrologic balance equation and then estimating the precipitation from that, backing it out. And both the interpolation method and the assimilation are giving you some negative numbers. And negative precipitation can't happen, right? Okay.
Q, E, and delta S are actually defined as?
Q is discharge in the river, E is evapotranspiration, and delta S is the change in storage from groundwater. Okay. And usually over long time scales, that's going to be small, right? So it's a way of backing out the precipitation estimate. And you hope that when you do that, your precipitation estimate ends up being positive, right? Okay. And in the case of the reconstruction for 12 years, 19 drainage basins, the numbers from the reconstruction are all positive, right? Whereas for some of the others, the reconstruction is showing negative values for some. So, and then we've got other stuff. So the way that we... Pardon?
Time is running backwards. I'm joking. Joking.
Oh, okay. Yeah. So the way we do this, again, this is another kind of computationally intensive problem, but this is, we can do day by day, so it's a pretty easy thing to move on to Azure. So we take the shortwave radiation estimate from the either the national or the global land data assimilation system. The upper left shows the resolution at which those data come in, which are, in this case, are 1/8 of a degree. We smooth those to the size of the MODIS pixel, and then we scale it based on the topography. So because the problem is in that 1/8 degree pixel, there's a lot of topographic variation, and so we scale it just doing a pressure scaling relationship. Then we bring in the slope and exposure, and then we calculate for attenuation by vegetation. We've got then a map of the albedo. We then estimate how much radiation, solar radiation is being reflected back upward, and what we end up with is a net. So that goes in, that's what energy that goes into melt. And then we do something similar with the long wave radiation, but in the interest of time, I'll skip that detail. But again, that takes a lot of computing, but that's pretty easy to parallelize because each day is independent of the other days. All right? And so if we do the same thing for the Hindu Kush, in this case, this is just showing the data for a day. We can get, over a mountain range that's very large. I mean, some of these drainage basins are, the Amu Darya itself is slightly larger than the state of Washington. It's 200,000 square kilometers. So we can get each of these inputs to the model over every pixel, and then we can calculate how much melt is coming from the radiation, what's coming from the sensible and latent heat flux, which is a function of temperature and humidity, and then we can get all the melt for a particular day, and then we can do it for every day for every year. And so this is showing the variability that we've seen in the years. 2008 is missing. This is my colleague Carl Ritker was running this on the Linux cluster at Santa Barbara, and there's a difference in Linux between the RM command and the MV command. And he typed RM instead of NV after he'd done all these calculations for 2008. But on the other hand, it made it an easier slide with only trying to put 4 years instead of 5. Okay, that's
the Hindu Kush here.
That's the Hindu Kush. Yeah. This is the Wakhan corridor up on the right. This is a sinusoidal projection that is it needs to be rotated a little bit. Okay, so I've learned how to use Azure sort of with Wenbing's help, and I think I've figured out how to deal with the hardest parallel part of the problem, which is the fact that we're dealing with something when you have, but it's a general problem of dealing with three-dimensional data where you want to sometimes slice this way and sometimes you want to slice that way. And then the rest of it is I think, easier to run in parallel, because once we do that, then we can run day by day. And
So the problems of mounting a disk on multiple servers.
you can't.
Yeah, that's the problem, right?
Well, I mean, now I'm wandering into territory where most of you know more than I do. But I guess the issue is that in the blob store, really what you can do is get and put. That you can't reach into the blob store and read part of a file. Okay, so you actually have to either, well, I don't know. I don't want to say it's too bad, because I'm storing these results as HDF5 files, which supports block compression, so that you can read a piece of it even though it's a compressed file. But you got to get it out of the store in order to read it. So I think the alternative is to take those chunks, that is to turn every image into a 9x9 or 3x3. So turn every image into 8 images, and then I can parcel those out to individual machines.
So this was all the calculations you needed to do to calculate the snow cover of this particular region for 4 years. And what do I learn?
Oh, okay. So what you now have is, let me maybe go back to this. Sorry about that. I think it was right at the beginning here. Yeah. So.
I missed this.
Okay. So what I've got is I've got methods in which I can estimate the snow cover during the year in real time. Because it's reconstruction, you get the answer, but you only get it at the end. On the other hand, what we show is it's a really good answer. Okay, and so what we now have is something that we can use to compare with, say, estimates from passive microwave, and with NOAA is developing a Central Asian snow accumulation model, but they have no way of validating it, and so this gives us a method of validation for that kind of a model. And so they're, in fact, I'm meeting with them toward the end of this month because they're really, they keep asking us, for the reconstruction results for the past decade as something they can compare. And then if we can figure out how to help with the passive microwave data, the advantage, as I showed before you came in, that only sees about 10% of the snow. Okay, but if we can figure out how to correct it, then that geophysical time series goes back to 1978. And so we can then do a better job of sort of putting any current condition into the historical as part of the historical narrative. Because a lot of what we can, I mean, in general, management of water works pretty well when you're kind of near the median, and so And so part of the idea with this is, can you identify the years that are at the two tails of the distribution? You know, is this?
Those 4 years you showed of the Hindu Kush look more or less the same.
Well, there was, in the Kabul part of the watershed, there was flooding in 2007. Yeah.
So I know where Kabul is on that map.
Okay. It would have been what's the part that's draining to the south, and that does show in 2007. So and by and large, one of the things that really helps in sort of management especially in places where simply giving a volume in cubic kilometers or acre feet or any sort of unit isn't going to mean much to anybody. But if you can put things in historical context, you know, if you can say that this year is say comparable to 2007 when there was flooding, or comparable to 2011 when there was drought, then even the villagers will remember what things were like in those conditions, and therefore you know, knew what got flooded then, or in the case of drought, how badly the crops did then.
And mobilize resources earlier.
And you can mobilize, yeah. Well, like, again, what happened in 2011 is there was a big drought, but
Can you show those? The final answer again.
Yeah, it's probably easier to. Okay.
So 2007 was a flood.
2007 in the southern part here was a flood. Yeah.
And the other, I don't see much difference.
Yeah. That's true. The interesting thing about that year and about 2011 is the snow-covered area was pretty similar, even though the depth of snow was different. So.
And the interesting part is like you said, layering that up with the basins where the water goes out of, and then also the populations.
Yeah.
So that you can use geoflow for. Anyway, thanks very much.
Good.